Welcome everyone to the session Functional Geometry in Swift and SwiftUI by Daniel Steinberg. We are glad, Daniel, you can join us today. Without any further delay, Daniel, over to you.
Hi, thank you. Let me share my screen. So I'm really glad to be here at Functional Conf. I was here in person in Bangalore years ago as I was starting to explore functional programming in Swift. And so I'm really glad to be here. And at that time and at this time, the question is, why does an iOS developer need functional programming? And some of the things that I'll show today, I implemented in Swift at the time, but SwiftUI, which is our UI framework, has made that even easier, which surprises some people. So there are obvious places where functional programming applies. Sequences, we have map, filter, reduce, and so on, and async sequences as well. Optionals are the maybe type that some of you know from other languages. Combine was our reactive framework, and that used a lot of functional programming ideas. And the surprising thing to many people was that SwiftUI also uses a lot of functional ideas. SwiftUI is our GUI. It replaces what we used to call UIKit or AppKit. It's the way of drawing things to the screen, and everything there is a value type. And that was our first hint that we were in a different world. It's not pure. I'm always afraid speaking at conferences like this that you'll say, well, that's not really, but you know, the IO monad, somehow when you do GUI, you need to make some exceptions. So I look at it as SwiftUI puts the fun into functional, and we won't be too strict about that. If you squint container views, these are our horizontal stacks, our vertical stacks. They're combinators. And although I won't talk a lot about combinators, when I implemented this in Swift years ago, we had to explicitly make combinators. These are sort of given to us in SwiftUI. So in this talk, I'm going to faithfully implement a 40-year-old functional programming paper using SwiftUI. And it's one of my favorite papers, and I hope you'll enjoy it. It's a paper by Peter Henderson from 1982. It's a paper on functional geometry. Excuse me again. He revised and he expanded it 20 years later. And mostly I'm going to refer to that 2002 paper. He did the earlier paper in sort of a Lisp-like language and the later paper in more of a Java-like language, but it was essentially the same ideas. So in it, he drew a fish, something like this. And he was motivated by the Escher pictures. And so that's what he was trying to get at. And he built a whole language around it using combinators. And again, I'm not going to dig into what do I mean by combinators. This audience actually knows. But more importantly, I think of it as a geometry language. And so if you draw a fish and then that fish has been rotated 180 degrees and you draw that at the same time, one over each other, then you do it like this. And this was in a second paper because that comma in the 1982 paper, there were no commas, but actually we could write that same code in the Swift programming language almost letter for letter. Now, that wouldn't be what we call Swifty. It would be correct, but it wouldn't be the way we write Swift code. We would tend to write something more like this. And this is the way we write visual code in Swift, where you see that I'm putting a fish and a fish that's been rotated 2 times, one over the other. What I like about this is this looks almost exactly like the original code that he wrote 40 years ago. I'm replacing Henderson's parentheses with curly braces, but other than that, it is exactly the same code. And so that's kind of what delights me about what we'll talk about today. And you get something like this. He also looked at 4 fish. He looked at 3 fish. You'll notice those fish are different sizes, and we'll look at all those transformations as we go on. And his eventual goal was this picture that was Escher's square limit. This is Henderson's rendering of it. You'll notice along the side that isn't quite a square, but he's approaching the square. That's the square limit. And I'm trained as a mathematician. In fact, I'm a geometer by training, so this I find delightful. So I'm going to begin with a circle. I know that a lot of you are not familiar with Swift and SwiftUI, so hopefully you'll catch on pretty quickly. We're going to end with a fish. And so there are lots of ways to think of a circle. SwiftUI itself has a circle. And so in SwiftUI, when we render a view, we do it by declaring a computed property called body. And body returns a single view. I don't know what its type is, and that's our keyword sum. It's going to return some view. In this case, I'm just going to return a circle, and when I run it, it looks something like this. And so SwiftUI out of the box, and this is the non-pure parts of it, there's a dialogue between a containing view and its child view, where the containing view says, here's how much space I can give you, and the child view says, here's how much I need. And so in this case, the circle takes all of the width, doesn't need all of the height. A circle is just a circle centered in the frame of that view that contains it. So that's our circle. There are container views in SwiftUI, and I mentioned the horizontal stack or the H stack. And the H stack allows us to put one circle next to each other. And in this case, you'll notice it's what we expect. I get a horizontal stack which says, how much space do you need? It splits it between the two circles, and it puts a little space between the circles by default. I can say, well, I don't want any space by saying spacing is 0. And notice the circles grew just a little bit to fill that space, and now they're touching. So my horizontal stack, my H stack, is this container view. And it's just a view that arranges things on a horizontal line, and that's how I got my two circles. You'll notice in the constructor for the H stack, you can specify the alignment, but by default, it centers things. It has some default spacing. We've set it to be 0, and that's what eliminated the spacing between them. And then the key is this view builder, this last parameter. And it is a function that takes nothing and returns the content. In this case, it returns the two circles. And what this essentially lets us do, because it's a function, we pull it out of the parentheses as a trailing closure. That's how we write it in the curly braces. And we don't have to put commas between them. That's what a view builder does. It allows us to write things in this nice form. And that's what's going to allow us to implement Henderson's picture language pretty faithfully. So although Swift people don't think of it this way, container views do use functional programming. And I'm going to come back to this later. So that's how we implement the circle in SwiftUI. In Swift, how do we implement it? Well, what sort of a language is Swift? We use it in different ways. People argue about the ways it's used. It's like looking at it from different perspectives, but many people came to Swift from Objective-C, so we came to it looking at it as an object-oriented language. Before Swift shipped, though, we got blocks or closures or lambdas, and they'd started to catch on. The syntax was awful. Objective-C syntax for blocks was just so bad that websites were launched with all sorts of curse words to tell you how to format a block. In Swift, they're just that trailing closure, just that closure, the curly braces around it, and it's very beautiful. So in Swift, it's very closure friendly. So we think, well, maybe Swift is functional, but the functional stuff felt like it was way over in the corner, like they didn't really care about it that much. And many people didn't embrace it. We had closures, we had map, we had filter, we had flat map, but in fact, for arrays, flat map was quite controversial because we had two flat maps, and one of the flat maps wasn't a flat map. And so the community finally realized they'd misnamed one, and we named one to be a compact map, and the one that was really a flat map stayed flat map. So we were using it without knowing what we were using it in a way. So what's a circle? When I asked people on my timeline to define a circle in code, most people gave me something like this. Some sort of a structure, either a structure or class that was a circle where it had a radius. Some people gave me an origin also to say the circle was centered over here. And so once you have your circle, What do you do with the circle? Well, the two things I think of doing with it is I want to draw it, or I want to determine if a point is inside the circle. And so I create an extension to circle, which which says, okay, I'm going to do something that is shape, and every shape should know if it contains a point. And if every shape knows if it contains a point, then for a circle, I just look at x squared and y squared, and that should be less than the radius squared. And functional programmers are losing their mind. A lot of you are looking at this and saying, oh, this is just so wasteful. They say that this is the shape. The shape is just the function that takes a point and returns a bool. And this is very foreign to Swift people. Looking at a shape as being a function, but actually I can define a circle, for example, provide a radius, and then my circle returns this function from point to bool. And again, for many Swift programmers, having a function that returns a function was very unusual. And so here's how we return it. Our closure is it returns a function that accepts a point and then checks if it's in the circle. So there's our function being returned that takes a point and returns a bool. We can easily check if a point's in a given circle. So I have a circle, or I take an annulus, I take a circle out of that circle, or I take a byte out of that circle. And this, of course, reminds us of this problem from DARPA from 1994. And this is something that appeared in the paper by Hudak and Jones. And many of you are familiar with it because they were comparing different programming languages, and Haskell did quite well. In fact, Haskell did so well that the people giving the test were suspicious. And so they famously taught a grad student Haskell for a week, gave them the problem, and they were the second place entry in this contest. And so that's described in this great talk by John Hughes, Why Functional Programming Matters. And also, it's the motivating example in Functional Swift, which is this book from the OBCIO guys. So once your shapes are functions, then I can operate on those functions, and I can find the points that are not in the unit circle by saying, give me all the points outside a circle of radius 1. And so I define that outside method or outside function by saying, you give me a shape, I'll return another shape. And again, this is very familiar to this group. The syntax is different, but I'm just reversing the Boolean. I'm saying, if you're outside the shape, I'll return true. If you're inside the shape, I'll return false, and that's my outside function. And so my annulus becomes the intersection of what's inside that bigger circle and outside the smaller circle. And I get the intersection of the shape defined as a point is both in the first shape, in other words, inside that circle of radius 4, and inside the second shape, which is outside the circle of radius 1, and that gives me the annulus. So what if we want to draw our shape? I won't spend much time on this, but one of the nice things that SwiftUI has is something called metal shaders. And what metal shaders do is they evaluate each point in the region, and they can tell using a true and false what color they should color them, or using a switch statement. And so in metal, which is more C-like, I would have a function like this where I draw based on the position passed into me. And if I'm in the annulus, I'll return one color. Otherwise, I'll return another color. And I've just skipped this part where I've re-implemented that Swift code in metal because it's more C-like, but it's the same exact functions and combining things. And so metal does that very quickly, and I can call that from SwiftUI using something called a color effect. And I ask my shader library to use that draw function, and I get that annulus. And so again, this pipes things right through the GPU. It's very fast. It's very forgiving. It's actually quite nice. And so that's, excuse me, the metal library. But I want a more SwiftUI solution. And so now that I've separated the code that defines the shape from the code that draws it, I can say a shape is a function. I have ways of getting a specific shape like a circle, and I have ways of combining shapes to get a new shape. I'm going to use those ideas and say, well, I could do those in object-oriented program, I could do those in FP, but that was a solution from 1994 that was so beautiful, was doing it in functional programming. And it turns out those ideas are related to that paper I mentioned before, that exploration from the 80s, which was Peter Henderson's picture language. And so he was exploring something he was calling functional geometry. And his original paper from 82 is very nice and very readable. And then he revised it 20 years later, as I said, and expanded it a little bit. And you might also know this from the structure and interpretation of computer programs from Abelson and Sussman, or from that Hughes talk. He mentions it there as well. So they begin with a painter. And a painter is a function that takes the frame that it lives in and produces output. And so there is the painter from the SICP book. It is this origin, which A defines, and then the two sides, which B and C define. It can be a parallelogram. I'm going to restrict it to be a rectangle because that's just simpler for me. And it's all that I need. And the frame is going to be a rectangle, but maybe it's tilted. Maybe it's not parallel to the axes, and you'll see that as we go along. So a painter is a function. And I said, in Swift, I'm going to take it from a rectangle to a path. And so you give me a rectangle, I'm going to draw a path in that rectangle. And so, for instance, if I want to draw the capital letter F, if you give me the bounding rectangle, I will draw a path, and I'll do it using this convenience method. Don't worry about this. What it allows me to do is say, you tell me how big the bounding rectangle is, and I'll start X 10% of the way across and Y 10% of the way down. It allows me to be relative to the bounding rectangle without doing all those calculations every time. And so if I add a line, I've moved across 90% of the way, still 10% down. And so I have drawn my letter F, and then I'll use that in SwiftUI, drawing the letter F, and I'll get something like this. Now, honestly, if I just type this in, I get an F that stretched from the bottom of the screen to the top of the screen. I've put this in a world that is of aspect ratio 1, so that there's the bounding square. And so you can see I start the F at the top left, 10% in on the X direction, 10% in on the Y, and my line across the top took me to 90% of the X direction and still 10% of the Y. So that's how I drew my F. We'll get to fish. So my painter is this function that takes that bounding rectangle and draws the path. And so if I split that bounding rectangle in two pieces, then I draw an F in each side, I get something that looks like this. And each side is a function from rect to path, and I bring them together using a function called beside, which takes two painters and returns a single painter. It takes the painter for each side and combines them. And so beside takes two painters, and it says, look, I'm going to return a painter, and it knows the bounding rect for everything. And it says, take the first one and cut that in half, the width in half, and draw that. And take the second one and cut the width in half and move it over. And now I've got one beside the other. And so this is how I draw one F beside another F. Not quite the syntax I want. This is the syntax of the 2002 paper, though. So I feel we've made some progress here. So I want to implement Henderson's picture language, but I want to do it in SwiftUI. SwiftUI is going to let me do this pretty easily without building all my combinators. I'll get them for free in a way from SwiftUI. And so the first four pictures he suggested were these: F, the rotation of F, flipping F in the horizontal direction, and then flipping it in the horizontal direction and then rotating it. So let's see if we can get these four pictures. The F we pretty much have, that F path that we had before, it just needs to know the bounding rectangle. And the way we do that in SwiftUI is we say, excuse me, We say the F curve is a view, and the view has a body. Remember, that's what returns the view that we're going to see on the screen. And it takes a geometry reader. And the geometry reader knows all the geometry of the box. And so one of the things it knows is, how big am I? How big is the box I'm in? And so that's how we pass the bounding rectangle into our F curve. And that's how it's going to be able to draw it in the square or in the square cut in half or whatever. And then I just stroke it. I'm going to let little f equal my F curve, and that allows me to just type F and get that picture F. Now let's rotate F. So now I need a view that accepts another view and does something to it. And so I'm going to define rotate, which is a view. It must have some view that it's rotating. I don't know what its type is. It might be the letter F. It might be a picture. It might be an image. It might be anything. And so we define a generic A, any view, and view is any view. And now in my body, I say take that view and rotate it by 90 degrees. And that's all I need to be able to say rotate the view F. And that's nice. It works, but it doesn't look like that code that Henderson wanted. He wanted us to write something like this. And so we have to make two small changes. The first change is I have to add an init that has this trailing closure that allows me to enter things in the curly braces. And the second thing I need is to type alias rotate to ROT, and now I can type ROT of F and I get this. And so SwiftUI is nicely so far allowing us to work with a single view. Flip is not much different. For flip, the only difference is what I do when I flip it, and that is I'm going to apply a scale effect where I reverse the X direction. Create a type alias for that, and that's all it took to flip it. Once I flipped it, I know how to rotate, and so if I rotate a flipped F, I get that, and I'm feeling pretty good. I'm able to work with individual shapes, and I can rotate and flip shapes. Maybe time for fish? Not yet. Henderson says, well, okay, you can work with one view. Can you work with two views? Can you put one view above another? Can you put one view beside another? And can you combine those? So combining two views, mostly the same. Over is going to put one on top of another, not above, but in the Z direction coming towards you. And so I'm going to need two views. And my views are going to be presented in something that SwiftUI has built in. It's called a Z stack. And a Z stack, like an H stack, a Z stack just organizes things so view A is drawn and then view B is drawn closer to you. I will type alias that. And so I need somehow to put that in the curly brace with no commas. And so I'm going to use an init. And my init is just going to be a way of sending that back. And the trick is going to be to use this thing that I'm going to call a to builder. And this is the key to making the rest of this work. It's called a result builder. And so my to builder is a result builder. Every result builder must have a method called build block in it. Might have more than one, but it has to have at least one. And this one is going to take two views. And it's going to accept two views, and it's going to return those two views. It's actually not going to do much, but what it allows us to do if we go back to our init is we're accepting a function, and we bring that function out as our trailing closure, and that allows us to write over with F and rotation of F this way. So I don't know about you and your languages, but what I love is looking at the call site, doing the hard work behind the scenes so that the call site is nice. And that's what we've got. Drawing one above another, it's just the above. And so I'll scale it, I'll shrink it in the Y direction, and I'll put one at the top, one at the bottom, and I'll type alias it. And that allows me to say above F and F. I'll do the same thing for beside. except I'll shrink it in the X direction. I'll type alias it, and now I've got beside. And if I've got beside, I can put those two things that are beside each other above another F, and I get this. So it's a geometry. There are rules. If I have an F and I rotate it, and I rotate it again, and I rotate it again, and I rotate it again, we get back to where we started. And so one of the rules is 4 rotations cancel each other out. You get back to where you started. So there are reductions in this geometry. Another one is if I start with one F above each other and I rotate that whole thing, I get the same thing as if I have an F beside each other, but first I rotate each F. And so there's another rule. There are tons of rules, and they allow us to have a whole geometry, an algebra even, where we can cancel things and build things and recognize when two things are really the same. Unfortunately, our next transformation isn't going to allow that, but before I get there, I want to specialize above and beside because excuse me, I need more from them. And so here's beside F and F. Here's what Henderson wrote as beside 1, 3, F and F. And you'll notice the ratio of the widths is 1 to 3. And so the scale is the left F takes up 1/4 of the space horizontally, and the right F takes up 3/4 of the space horizontally, 1 over 1 plus 3 and 3 over 1 plus 3. And so we'll redefine beside by taking this hard-coded half and replacing it with whatever the scale is, and we'll calculate the scale down in the init by saying, you give me that 1 and that 3, and I'll calculate the square as 1 over 1 plus 3 and 3 over 1 plus 3. And so that's how we get the scale. And by default, they're 1 and 1. So by default, it does take up, each one takes up a half. And so beside 1, 3 looks like this, and beside still looks like this. Now, that brings us to our last fundamental function, and it is this rotation 45. And this is a weird one. I'm going to scale in each direction by root 2 over 2, which should stir little trigonometry memories inside your head, especially when you see that I'm rotating by 45 degrees. And so that's a rotation which sort of spans, now the diagonal spans that old width. I'm going to type alias it, and so I've left the original F so you can see that actually this transformation takes us out of the box. It takes us out of the frame, out of our world. And so Henderson recognized that it's an outlier. It doesn't fit in with the geometry. I can't do my reductions. But he wanted to draw fish. And so let's look at the fish. To draw the fish, we start with a fish base. We use our basic rotations and besides to get the vertical of the fish. You can see how the base turns into that vertical. And now I've got most of the fish. I'm going to draw this diagonal, the top half of the diagonal. This uses a rotation 45. You can see that it's that vertical piece shrunk and rotated some amount. And now here's the rest of it. And because we constructed it from that base using all these transformations, this fish has a lot of symmetries. And so this fish will fit into itself in many different ways. It's basically built around a 45-45-90 triangle, so I can tile the plane with it. And we draw the rest of the fish so it looks more like a fish. That looks better. And so now we can have some fun. We have our basic pieces. If I take my fish and I rotate it 180 degrees, 2 rotations, and put it over itself, I get this. If I get rid of that top fish and I shrink it and rotate it, I get this guy. And if you look at the top, it's begging for another fish to be put in there, and there's my 3 fish. If I get rid of the big fish, this is begging to be rotated, And now we get the 4 fish. So we've got our fundamental building blocks, our 2 fish, our 3 fish, our 4 fish. I also need something called a quartet. And so if I have a quartet of a circle, a rectangle, an F, and a fish, it looks like this. What you can see is this is the circle and rectangle beside, and the F and the fish beside, and the first beside above the second beside. And so a quartet is just an above of 2 besides. There's a special quartet called a cycle. The cycle takes a single view and does the above and beside, but it rotates it as it goes around. And so the cycle of F looks like this. And now I can use the quartet to start with this, our 4 fish, and build a quartet of this. And now I get something that looks like this. And it's that moment in programming where you've built all your work, you've done all the hard stuff, and now it's starting to pay off. If I start with my 3 and I build a cycle from the 3, I get this, and now I'm beginning to see the limits. I just need something above and below, and I just need to start building it out. So I need 4 sides, I need 4 corners, need just a little bit for that. I'm going to build a body. I'm going to use that above 1, 2, beside 1, 2, because going back, notice the height of the side is not the same as the height of that centerpiece. It's like 1/3 of it. And so I'm going to build it out this way. I'm going to repeat view Z here just so you can see the symmetry. And so this is the piece that I'm going to build out. So I need a side. Here's my side. It's 2 empty views on top of the quartet. It's the 3 fish and a rotation of 3 fish in the bottom, and I'm going to keep that. The bottom will stay the same, but as I iterate, I'm going to replace the empty views with side 1 when I go to side 2. So there's side 2. And when I iterate, I'm going to replace those side 1s with this, with the side 2, and you can see it start to fill out. And I'm going to do the same thing with the corners. I'm going to start with 3 empty views and 4 fish in the bottom right. The 4 fish will stay the same. The empty views will be replaced with a corner, a side, and a rotation of the side. And the only thing happens as I iterate is I take those pieces and I go from corner 1s to corner 2s and side 1s to side 2s, and I start building it out. And now I'm ready to put everything together with a no net, a 9-piece. The 9-piece has my 4 fish in the middle. It has my 4 sides. I just start and I rotate each one. It has my 4 corners. I start and I rotate each one. And I build it out like this. I add my side, I rotate it, I rotate it, I rotate it. I add my corner, I rotate it, I rotate it, I rotate it. And I just love this. With SwiftUI and functional geometry, we've recreated this paper from 1982 pretty simply, and we get our fish. So I find that pretty stunning, and thank you. I'll post the code, clean up the code a little bit and post it and on GitHub somewhere.
Thanks, everyone. Thanks for joining. Thanks, Daniel. Let's meet at Hangout section. Bye.
Thank you. See you there.